Welcome to another deep dive. Before we immerse ourselves, just want to let you know that this deep dive is from the podcast series AI 10X, brought to you by 10 Leaves. Today, we're navigating a frontier that, honestly, feels cold straight from science fiction, but is rapidly shaping our reality: brain-machine interfaces, BMIs. And look, this isn't just about controlling a computer with your mind anymore. We're seeing, well, remarkable progress from restoring senses to maybe even augmenting cognition. We're talking about a field right at the dynamic intersection of AI, neuroscience, and advanced biotechnology. It really promises to fundamentally redefine how we interact with technology, maybe even each other. To help us unpack these intricate layers, we're joined by our expert. So, okay, we've all heard the term brain-machine interface, but for our listener who likely follows this space, let's maybe go beyond just the basic definition. How do these systems truly establish that dialogue with our brain, our most complex organ? What's the sophisticated dance happening there between biology and silicon?
That's a really good way to put it, the dance. Fundamentally, BMIs are intricate communication systems. They're designed to create a direct bridge, like a bidirectional pathway, between the electrical buzz of your brain and some external device. It's about translating the brain's own language, those electrochemical signals, into commands machines get, and sometimes actually feeding information back to the brain, too.
Feeding it back. Okay, that's interesting.
Yeah, and what's fascinating is just the sheer ingenuity in how we capture those neural signals. I mean, we're not just talking broad stroke brainwaves here. For the really sophisticated interfaces, we're dealing with very specific sensor types. So on the less invasive end, you've got EEG, electroencephalography.
Right, the caps with the electrode.
Exactly. Electrodes on the scalp, they're pretty good for general brain states, like, detecting an intention to move something. But the signal quality, well, it can be limited. The skull and scalp get in the way a bit.
Muffles it, sort of.
Right. So to get truly granular control, researchers often turn to more invasive methods. We're talking ECOG, electrocorticography.
ECOG.
Yeah, that's where a grid of electrodes sits directly on the brain surface but still under the skull. That gives much clearer signals.
Okay, closer to the source.
Definitely. And then, at the real bleeding edge, you have things like intracortical implants. Think of the well-known Utah array.
Ah, yes, I've heard of that one.
It's this tiny grid, hundreds of microneedles, super thin, penetrating just a millimeter or two into the brain's cortex. These arrays can actually record the activity of individual neurons. That offers an incredibly rich, really precise data stream.
Wow. Individual neurons. So it's really about choosing the right tool for the job, isn't it? Trading off how invasive it is for how precise the signal is.
Exactly that trade-off.
But okay, once you have all this data, this cascade of electrical impulses, how does the AI actually decode it? You called the brain a noisy symphony earlier, which sounds right. How do you pick out the signal, the intention, from all that noise?
You've absolutely hit on the biggest technical challenge right there. That noisy symphony is spot on. The AI's job is basically to listen very intently. Imagine trying to pick out one specific conversation in a really crowded stadium. That's kind of the scale of the problem with raw neural data. So when you intend to move your hand, specific groups of neurons, say in your motor cortex, they fire in a unique pattern. The AI, and this often involves advanced deep neural networks, other machine learning tools, it's trained to recognize those specific patterns.
So it's pattern recognition, essentially.
Highly sophisticated pattern recognition, yeah. It's not just translating a single thought, it's learning the correlation between a complex firing pattern, maybe hundreds of neurons, and a desired outcome. So for example, we show the AI what your brain activity looks like when you imagine moving your left arm versus your right arm. It builds a statistical model from that. And that model then predicts in real time what your intention probably is based on the neural signals coming in. The real sophistication, though, comes in training these models to adapt, because everyone's brain is slightly different, right?
Right.
And they need to continuously improve their accuracy. Often that happens through feedback loops. The system literally learns from your successes and failures in controlling the device.
So that's the calibration phase you hear about.
Precisely. It's the AI essentially learning your unique neural vocabulary for action. It's a dialogue.
That real-time learning, yeah, that's critical. It really highlights this isn't just a static translation device, it's dynamic. So, with all this incredible sophistication, where are we seeing these technologies making a real, tangible difference today? Are they still mostly stuck in research labs, or are they genuinely transforming lives now?
Oh, they're absolutely transforming lives already. The most profound, the most immediate impact of BMIs has definitely been in assistive technologies for individuals with severe disabilities.
Like paralysis.
Exactly. Think about people paralyzed from spinal cord injuries or perhaps neurodegenerative diseases like ALS. For them, BMIs can offer a genuine lifeline back to independence. We've seen some incredible demonstrations, especially with advanced prosthetics.
The robotic arms.
Yes, exactly. Individuals controlling sophisticated robotic arms. I mean, prosthetics with multiple degrees of freedom, allowing for really precise grasping, manipulation just by thinking about moving their own missing arm. Landmark clinical trials like the BrainGate project have shown people with paralysis able to move a cursor on a screen, type messages, even operate complex software.
Just by thought.
Just by thought, it effectively gives them back a voice, agency. It's quite profound.
Yeah, that's amazing.
And it goes beyond just control, too. Think about patients with locked-in syndrome. They're fully conscious, but completely unable to communicate verbally or physically. BMIs are starting to allow them to spell out words or maybe communicate simple yes or no just by focusing their thoughts. The system decodes that focus into text or synthesized speech. It's providing a fundamental human right, isn't it? The right to communicate, which was previously just denied to them.
Truly remarkable. Restoring communication, restoring movement through pure thought. Okay, so beyond these really life-changing assistive devices, what else is happening? What's on the cutting edge? We hear about ambitious projects, but what are the more experimental frontiers maybe pushing things even further?
Yeah, that raises the important question, what's next, right? In the research labs, we've certainly seen those captivating demos, monkeys playing video games with incredible precision, just using their thoughts.
Right, Pong and things like that.
Exactly, showcasing the potential for really fine motor control. But maybe even more compelling are the efforts trying to restore sensory function.
Senses, like sight or hearing.
Precisely. It's incredibly challenging. But some researchers are exploring how BMIs could bypass damaged optic nerves or damaged cochleas in the ear. The idea is to directly stimulate the brain areas responsible for vision or hearing. Imagine directly transmitting visual data from a camera, say, straight to the visual cortex, restoring even rudimentary vision that way.
That would be revolutionary.
Absolutely. And then, of course, you have projects like Elon Musk's Neuralink, which gets a lot of headlines.
Yes, definitely.
Their approach is kind of unique in its sheer scale. They're attempting to implant thousands of these tiny, flexible electrodes, they call them threads, directly into the brain. And their goals are ambitious, extending beyond just basic control. They talk about restoring full mobility to paralyzed individuals, even vision to the blind, by leveraging this really high bandwidth connection.
Thousands of electrodes, that's a different level.
It's a very different approach, yeah. Both in scale and the implantation method compared to earlier tech. Really pushes the boundaries of what's surgically viable and how much neural data we can realistically capture and process. It's really a testament to how rapidly this field is moving, Both traditional research labs and these big private ventures are pushing the envelope hard.
The idea that we might restore sight or directly connect to literally thousands of neurons,
Yeah.
it is mind-blowing.
Yeah.
But okay, every groundbreaking technology, especially one touching the very essence of being human, faces huge challenges. So beyond the technical wizardry, what are the major hurdles, the things we really need to overcome to make BMIs more robust, more widely accessible, and truly integrated into society?
Well, the biggest technical challenge, as we kind of touched on, it really centers on getting absolute accuracy and, crucially, long-term reliability. Neural data isn't just noisy, it's also highly variable. It can change over time because our brains are plastic, they adapt.
The brain rewires itself.
Yes. Exactly. Your brain might adapt its firing patterns as you learn or just as you age. So the AI models, they need to constantly recalibrate. They need to be robust enough to handle those changes, ensuring that a system always understands your precise intention without misinterpretations, especially in critical applications like controlling a wheelchair or a prosthetic. That's a monumental task.
You can't afford errors there.
No way. And the real world is far less controlled than a lab. So getting robust performance in diverse, unpredictable settings, that's crucial.
Okay, so reliability is key. What else?
Another significant hurdle is just the longevity and the biocompatibility of the implanted devices themselves. The brain is an incredibly delicate environment. It's also surprisingly hostile to foreign objects. Over time, the body's immune response can kick in, lead to scar tissue forming around the electrodes.
Which degrades the signal.
Exactly. It degrades the signal quality. So we need materials, we need designs that can last for potentially decades inside the brain without causing harm or losing their effectiveness. That means constant innovation in material science, in surgical techniques.
Those technical and biological hurdles sound immense. And then, as a society, we also have to grapple with the really profound ethical implications, don't we? If we're talking about direct brain access, what are the core ethical conversations happening right now?
You're absolutely right. The ethical dimension is just as critical, maybe even more so than the technical one. One of the most immediate concerns is the privacy of thought.
Mental privacy.
Yeah. If a device can decode your neural signals, even your intentions, where does the line between a private thought and accessible data actually lie? Who owns that data? How do you secure it? The very notion of mental privacy, something we currently just take for granted, it becomes this incredibly complex legal and philosophical question. Regulators are already grappling with how to define and protect this completely new form of personal data.
That's a huge one. What else?
Then there's the whole issue of informed consent, particularly when you're dealing with invasive brain surgery and technologies that could potentially alter cognition or even personality down the line.
How do you ensure someone truly understands the risks and benefits?
Exactly. Especially for vulnerable populations who might disproportionately benefit but could also feel pressured into using these technologies. How do you ensure true informed consent? And then, of course, there's the potential for misuse. Any technology with this kind of profound power carries the risk of being used for unintended, maybe even malicious purposes.
Like surveillance. Or worse.
Surveillance, manipulation, you name it. These aren't just theoretical debates anymore. They're active discussions among neuroethicists, researchers, government bodies. They're trying to proactively establish frameworks, guidelines before these technologies become widespread.
Building in the guardrails early.
Exactly. It's about building in those guardrails as the technology develops, rather than just reacting after problems inevitably arise.
It's clear that navigating all this requires not just scientific brilliance, but also some really deep societal reflection. Which leads us, I guess, to the grand vision. What could this mean for the future of human potential? For how we interact with the world, assuming we can responsibly address these really complex hurdles?
Well, if developed responsibly, and that's a big if, with robust ethical frameworks firmly in place, the possibilities for enhancing human potential are, frankly, transformative. We could see entirely new forms of human-AI collaboration, where our minds interface directly with artificial intelligence, not just through screens and keyboards like now, but as truly integrated systems.
Integrated systems.
Yeah, imagine a designer being able to mentally sketch a 3D model, just think it into existence, or a scientist visualizing incredibly complex data directly in their mind's eye, with an AI maybe assisting their thought process in real time.
So it's not just about control, it's about co-creation.
Augmentation.
Exactly. Co-creation and augmentation of our actual cognitive processes. And then think about cognitive enhancement itself. Now, this is more speculative, obviously.
Yeah.
But the ability to directly access vast amounts of data, or maybe even accelerate certain neural processes, could it mean thinking faster? Learning new languages, complex skills in a fraction of the time, recalling information with perfect clarity.
Like memory upgrades.
That's the idea behind memory augmentation, yeah, where an external system could seamlessly integrate with our biological memory. Or, taking even further, maybe enabling forms of direct brain-to-brain communication, where ideas, maybe even raw sensory experiences, could be shared directly between individuals.
Yeah, that's a whole different level of connection.
It's a paradigm shift, isn't it, in how we learn, how we communicate, how we leverage intelligence, both biological and artificial. And we connect this to the really big picture. BMIs could fundamentally rewrite the rules of interaction, of learning, and even, in the very long term, maybe influence human evolution itself.
Evolution.
It changes our perception of biological limits, doesn't it? It opens up pathways to interact with technology and with each other in ways we've literally only dreamed of until now. The interface isn't just external anymore, it's becoming increasingly internal, blurring those lines in fascinating and, profound ways.
Incredible possibilities ahead, definitely. And such crucial insights to consider as well, both the exhilarating potential and the critical challenges we face. Thank you for this deep dive. That wraps up another deep dive from the podcast series AI 10X, brought to you by 10 Leaves. The idea that we could be developing technologies that fundamentally rewrite the rules of interaction, learning, and possibly even influence human evolution. It really is a lot to think about. It makes you wonder how these interfaces might reshape our very understanding of what it means to be human in the coming decades. Until next time, stay curious, stay informed, and keep exploring the frontiers of technology.